Hi there, I'm Stephan Lavavej, a Visual C++ Libraries developer, and today I'm starting a new series called Core C++. So in previous series, I introduced you to the standard template library, which contains things like vector and algorithm and whatever, and then there was an advanced STL series. But these libraries are implemented on top of what's called the C++ core language. The core language is the part of C++ that you can use without including any headers whatsoever. It's always there, always available. It's the things like classes and virtual functions and using directives and templates that libraries are built on top of. It's sort of the relationship between the core language and the standard library is like between physics and chemistry. You know, chemists, they are built on top of physics, and they need to know physics even though they're not really physicists. So I'm very much like that. I'm a library developer. I write and maintain libraries for a living, but I still need to know a lot about the core language if I want to get my job done. Not just to understand hideous compiler errors, but also how to express myself. Very often times people will come and mail to our internal C++ mailing list saying, hey, how do I do X? And if you know enough about templates or name lookup or whatever, it's very possible to write a very convenient solution in C++ that wouldn't be possible otherwise. The core language it's really large. There's so many things going on in it. It can seem sort of overwhelming. So in this series, I'm going to be walking through various topics, starting with name lookup in this part, but then going on into overload resolution, template argument deduction, and any other topics that you want to suggest in the comments. So let's start off. What happens when you call a function in C++? If I just say something like foo of 1122, what happens? Well, the compiler needs to know a lot of things. It needs to know which foo you want. And this is also true in C, but in C++, it's so much more expressive, and that means that there's a lot more going on in the core language. First, the compiler has to do name lookup. It sees, oh, you said foo 1122 like this. You want some function foo. Which foo do you want? Is it in the global namespace? Is it in another namespace like namespace stud? Is it in a subnamespace of that? Is it a class member function? Maybe I'm within a member function of a class bar. And when I say foo 1122, I'm not calling some free function. I'm calling a class member function. Do I want that one? Do I actually want to do argument-dependent lookup? Now, if the arguments are 1122, the answer is no. But if the arguments are of class type, maybe it is. This is also true in the case of operator overloading. If I say something like s plus meow, this is an overloaded operator on std string. And the way C++ does operator overloading is that it's just pretty syntax for an ordinary function call. This is just another way of writing operator plus of s and meow. So it still has to do name lookup to figure out where this operator plus lives. Which one do you want? So once it finds all the possible names that you could potentially want, then all of these names get thrown into the overload set. But wait, what if one of those functions is a template? Maybe I have something like, if I say template on type name t, type name u. This is totally unrealistic. Void foo taking a const tref t and a const uref u do stuff. Name lookup will find potentially this function template foo in the global namespace or wherever. But you haven't given it explicit template arguments, which is good. You shouldn't usually give functions explicit template arguments. But the compiler has to go fill them in and to generate function signature that you can actually call. Because a function template is like a cookie cutter. You can't eat a cookie cutter. It's made of metal. But you can use it to stamp out cookies, and cookies are delicious. So the compiler wants to stamp out an ordinary signature. That means it needs to do, potentially, template argument deduction. Obviously, this does not happen for plain old functions. They just get thrown into the overload set. So once template argument deduction is performed for any functions that might have been found, and that can either succeed or fail. If template argument deduction fails, then nothing is added to the overload set. That's that crazy rule called substitution failure is not an error. Sphine, there's like a zillion ways to pronounce that. Then what the compiler does is overload resolution. It says, okay, you've got free function foo in the global namespace. You got a std foo. There is no std foo. You've got some function templates that have generated exact signatures. Which one is the best? And overload resolution has a bunch of subtle rules. It's intended to produce a desirable result. So if I've got foo taking int and int, and another foo taking constring ref, and my arguments are 11 and 22, then I obviously want the ones taking, the foo taking a couple of ints. The one taking a couple of strings is just totally unsuitable. So overload resolution has rules that will select the desired overload by comparing the argument types against the parameter types. It's just playing this little game of, okay, could I possibly call this function? That's sort of the first step. And then, is this function the best one? There's this concept of a best viable function. Sometimes, though, the result is ambiguous. If I've got a foo taking long and another one taking, say, short and short, and my arguments are int and int, that's actually ambiguous. The compiler looks at that and says, you know, I could convert one way, and I could convert the other way, but I consider them both to be equally good, and I'm just going to throw up my hands in the air. I'm going to say, hey, this is ambiguous. Usually, the compiler is right that it really totally is ambiguous. Sometimes it could really select a good one, but the rules have been stated in such a way that the compiler says, okay, I need additional help from you, the programmer. I need you to insert a cast, or otherwise clarify which function you possibly want. So after overload resolution happens, then there's actually access control. This is performed surprisingly late in the process for very good reasons. So one of the things, as I'm a chemist, not a physicist, when I look at the core language, I look at it from the perspective of, okay, here's this core language handed down to me by the committee. I want to understand how it works and how to write programs using it, and then how those programs could potentially misbehave, so I can either diagnose compiler errors or structure my program in such a way that I can avoid triggering undefined behavior or unspecified behavior, like the unspecified order evaluation or whatever. I don't usually question why the rules are structured the way they are, because I can't usually immediately see a rationale for it. I like to say that in the standard library, things sing to me. If I see something in the standard library, I know why it's structured that way. Even if I don't know, if I haven't already been told the rationale, I can figure it out for myself. The core language, for whatever reason, it doesn't sing to me like that. So I just usually say, you know, these are the rules the way they are. You know, I believe that they've been designed good, but don't ask me for the rationale. In the case of access control, though, there is a reason why it's performed so late in the process, and I am aware of the reason, so I don't need to speculate. And it's sort of a deep principle that making a function public or protected or private shouldn't affect which function could possibly be called. That would be very strange. If we had a class where all of its member functions were public, and then we look at that class and we say, oh, you know, nobody else really needs to see this, you know, meow function that I have. I can go make it private. If making it private had any effect other than transforming code that used to compile into a hard compiler error, if instead it could affect the result of overload resolution and make the code still compile but call something totally different, that would be very strange. And it would actually be a gotcha. C++ is full of enough gotchas already. So when the language was designed, I believe it was Stroustrup who said, you know, access control needs to be applied as one of the very last steps. After finding all the possible names that could be called and running template argument deduction and overload resolution, once we pick a winner then we see if we could possibly call that winner if we have sufficient access to it. And then finally, it's not even really a step here, but it happens at runtimes anyways. Then there's virtual functions. So just because I found a particular function to call and I have access to it, that may not be the function that I actually invoke. It is quite possible in a class for a function to be overridden, and even though users don't usually write code like this, you can easily have a public virtual function that's been overridden by a private virtual inner-derived class, and that one will actually be called. The way I like to put it is virtuosity is orthogonal to access control. But that's specific to classes. It doesn't affect free functions, which are never virtual. So I want to start by looking at name lookup in this part because it is surprisingly tricky when you start looking at all the subtleties. You can go potentially for years without really looking at all of the ways that name lookup works. But if you want to really understand what's happening, that's when you start consulting the standard. So I've got a copy of the current working paper. As of this date, it's N376 open. You can access this for free at WG21's website. That's the standardization committee. And the way that the standard is organized, which I've previously shown in the Intro and Advanced STL series, is it's organized into a bunch of clauses. Clause is the standard term for these big numbered sections, like 3 basic concepts, or 5 expressions. Every expression you could possibly ever write in C++ is covered in this clause. So a clause is big. It is huge. It's got all these little subsections like 5.1, 5.3, and so forth. So the standard starts off with all of the core language clauses, classes, derived classes. There's a whole clause just for overloading, another one for templates. And around clause 17, that's when it switches to the standard library. So all of the later clauses in the standard, 17 through 30 in this case, these cover the standard library, and it's the first ones that cover the core language. They reference each other, of course, but it's usually in the direction of the standard library referencing the core language. The core language almost never references the standard library, and then we've got some appendices at the bottom. So they're not quite organized in the order in which, say, a function call works. Although in this case, name lookup lives under clause 3, 3.4 name lookup, so I'll be pointing to that one. And also namespaces live under clause or section 7.3 namespaces. You can see it's kind of scary how I can just know which section something lives in. Like I know that even without looking, it's 14 that's templates and 5 that's expressions, that sort of thing. After a while, you start to internalize the standard, but early on, for the first few years, search in the PDF was my constant companion. So for name lookup, one of the things that makes name lookup tricky is this concept of namespaces. We all sort of know why namespaces exist, but just to go over it again. In C has no concept of namespaces. Everything lives in what C++ programmers consider the global namespace. What happens if, and that's fine, like for small programs, it's fine. You've got, just, a few thousand functions. And if you are, or your programmer team can decide on what function should be called, there's no risk of collisions. But that starts breaking down as soon as you go to larger and larger programs that are built of libraries. Library A decides it really wants the function name sort. What if library B also wants that function name? They were developed independently, perhaps at totally different times, separated by years. And then some program C decides, oh, I want to use both library A and library B. But wait, they both define this function called sort, and they're both trying to call this function. And hey, what if my own program has a function called sort? What do I do? So as a defense, C libraries will often prefix all of their function names and data structure names with the name of the library. Like zlib or bzip2 will prefix it with z or bz, that sort of thing. And that's kind of crummy. Why do we need to sort of infect all of our function names with this prefix just to avoid collisions? Wouldn't it be great if we had a language feature that could avoid that? So that's why namespaces were developed. The idea is that every library will define all of its functions, all of its classes, and other tech inside a namespace, and only that namespace needs to avoid colliding with some other library. Usually that's pretty easy because the name of the library is relatively unique. And we see this in namespace stud. The std namespace is where all of the standard library lives, with only a couple sub-namespaces like stud placeholders now for bind. And somebody else can easily define their own sort function as long as it's in a namespace not called stud. And this allows them to coexist side by side, and the programmer can distinguish between them. So, however, the fact that we've got all these functions living in namespaces means that the program needs to be able to access code living in those namespaces, and that's where name lookup comes in. So there's sort of three major forms of name lookup. You've got your unqualified name lookup. That's like when you've got a foo 1122. If there's no qualifiers to the left of it with double colons, then the unqualified name lookup rules activate. Then there's qualified name lookup. That happens if I said something like stud double colon sort. In that case, I'm explicitly saying, hey, I want to go reach into the stud namespace and then pull out the sort function. I don't even want you to consider any other namespaces that might contain sort functions. And finally, there's argument-dependent lookup, which is sort of the trickiest part. It's surprising. Sometimes I'll be on, a mailing list or forum, and I'll say, oh, you just use ADL. And programmers are like, wait, what's ADL? Because it is a relatively advanced feature. Early on, it was known as Koenig lookup after Andy Koenig, who had invented this. And for a long time, it was actually marked as such in this helpful name that each section of the standard is tagged as. One of the few times any feature in C++ was named after a person instead of a description of what it is. That was actually changed in C++ 11, and now it's actually tagged as argdep or ADL. Instead of Koenig lookup. But if you're ever looking at an old FAQ and something refers to Koenig lookup, it really means argument dependent. And then after all of the possible names that a function could be living in have been found, that's when the other sections of template argument deduction, overload resolution, and so forth activate. So let's switch over to VC for now. I'm still running VC 10 SP1. I should install the VC 11 at some point. It's not yet RTM. And here I've got my example hello world or meow program where I've got this using directive, and I'm saying using namespace stud. This is known as a using directive that will drag in all of the names from the target namespace, and that allows me to say cout meow and all like this. So what if I didn't say using namespace stud? Will this compile? It will not compile. In fact, I'm going to get squiggles. Thank you, IntelliSense. It's going to say error. Cout is undefined. I don't know which one you want. So I would need to say stud cout and also stud endl. Yes, thank you, IntelliSense. I know what I'm doing. Like this. And the squiggles go away, and this will actually compile. And if I run it, it'll work. So this itself is using argument-dependent lookup. And remember when I said that overloaded operators in C++ are just pretty syntax for a function call? Well, look at this. Stud cout left shift meow. This is a function call. The way it's really interpreted by the compiler, I'm just going to get rid of this endl for now. Imagine I'm just going to print meow. I can even put a \n there like this. I could have written this, even though nobody does, as operator left shift stud cout comma meow. Just a string literal. Okay, so I needed to qualify cout with stud because that's the namespace that it lives in. Yet I didn't qualify operator left shift. Here I could have when I'm writing its full name, but when I'm just putting it inline, I have no opportunity. You can't say stud double colon left shift. That would be weird. And yet this compiles and runs. How does this possibly work? Because this operator itself lives in namespace stud. Yes, it worked. And the reason why is argument-dependent lookup. So that's why C++ has this rule. It says, OK, if you've got an unqualified function call, like this operator left shift, but it applies to plain functions as well. Overloaded operators aren't special. In addition to ordinary unqualified name lookup, I want you to look into the namespaces that the the function arguments live in, hence argument dependent, and also search those. Throw everything into the big cauldron, and then run overload resolution and let a single winner emerge, or declare an ambiguity. So this is how operator left shift can be defined in namespace std, isolating it from other namespaces, boost or whatever, and yet be found through pretty syntax. So this is one of the primary reasons ADL exists, but it's not the only reason. Things like non-member swap or tightly associating a non-member function to a class are the reasons why ADL exists. Now, ADL does have its own gotchas. It's certainly not the cleanest behaving C++ feature, and it's also relevant in the C++ 11 range-based for loop. If you watched my Going Native 2012 presentation, at the end of the slides, actually in the bonus slides section, because I didn't get to cover it, when you write something like, let me show this. If I say include vector, and I have a vector int v, this will not compile because I'm still running v10. I'm just writing some code here. And if I said something like for autoref e in v, the range-based for loop has a bunch of rules that say, okay, let's look at this. Is it a built-in array? No. Does it have begin and end member functions? Yes for vector, so it's just going to call them. Otherwise, if it's just some other type, it's going to say, I said something like range here. If it doesn't have begin and end member functions, notionally, it's going to have non-member calls, begin range, and end range to get those iterators. So how does it find begin and end? And the answer is it uses argument-dependent lookup. And in fact, just at the last standards committee meeting in February in Hawaii, the core working group resolved an issue exactly how is ADL used here, and the answer is it uses this sort of thing called pure ADL. It will only search the namespaces associated with range, and it will not do unqualified lookup. It turns out that you actually can't get this effect in just plain old C++ if you've got a certain scheme of using directives. That means that if you want to associate a non-member begin and end with some type, it really does need to be in the same namespace as that type. You can't stick a begin and end in the global namespace and expect them to be invoked, or you can't stick them in a helper namespace and expect that a using directive will drag them in. This is interesting because when I first looked at the wording for the range-based for loop, I just assumed that it would be using ordinary ADL. Every other compiler writer outside Microsoft assumed it would be using pure ADL, and that dispute was resolved in time for us to fix it in VC11. So VC11 RTM has already implemented these pure ADL rules, so that's what you'll see. Just one example of how these rules can get more and more complicated, and yet they're used to power something that's ultimately very simple. Like when I write a range-based for loop, I'm not really worrying about how it's finding that begin and end, but the compiler must know exactly how to find a begin and end. That's why the core working group has to resolve issues that might seem very fiddly and extremely obscure to most programmers, but they do matter, especially to library writers like me who are always trying to do complicated and tricky things. So one thing, actually a couple things that I always see people confused about are namespace aliases in addition to using directives and using declarations. Sometimes I'll write the syntax and people will say, wait, what is that thing? Is that new to C++ 11? And the answer is no. No, these things are actually old. They were in C++ 98. So imagine that I've got namespace foo, and then nested within namespace bar, and then namespace meow, like this. And then I've got a class kitty. Or it could be, concurrency, parallel algorithms, Windows Foundation collections, whatever you got. Not every namespace is as convenient as std, only 3 letters. Now, I can always refer to this thing using explicit qualification as foo, bar, meow, kitty. In part 2, I'm going to be making nothing but cat noises. Like this. But this is horribly verbose. I had to say all these double colons. Yeah. Now I could use, I'll get to the using part, but if I still want to be clear where I'm getting this class from, it could be a class, it could be a function, whatever, but I just don't want to be so verbose. For types, we have typedef. So I could, once and for all, I could say typedef, this thing, as say f, b, m, k, and then wherever this lives, the global namespace or wherever, now I can just refer to fbmk, this fake name, and it's really a typedef for this particular type. So that works for classes. But what if I had to do this for like 10 different classes? Should I make typedefs for all of them? That's kind of lousy. Or what about for functions? I can't typedef a function. That doesn't make sense. It's a typedef. So C++ 98 has this thing called namespace aliases. Instead, what I can do is I can say namespace fbm equals foobar, yeah, like this. And then later on, I can say, oh, I want an fbm kitty. Or I could use qualified lookup to do something like call fbm feed my kitty, like this. Call this k. So when I say namespace fbm equals some horribly long namespace, this is what's known as a namespace alias. You can think of it as a typedef for namespaces. So fbm is just a quick way to say foo, bar, meow. It only works for namespaces. You can't put like classes or anything in there. And then I can use that to refer to classes or functions within that. I'm a big fan in C++ CX of immediately defining namespace aliases for Windows Foundation collections and platform collections, because that's horrible. I'm not going to type more than 5 letters for a namespace. I would much rather say WFC and PC. So if you're ever faced with obnoxiously long namespaces, especially nested ones, consider using namespace aliases to make your code cleaner, easier to read. So as for usings, there's actually 2 ways to do using. Okay. There is using directives. And this looks like using namespace stood. And then there's using declarations. Okay. And this looks like using stood vector. This is the one that most people see on day 1 in their Hello World programs that simply drags everything in. So a using directive says, I want to take all the names in stood and drag them out. That's how I think of it. I'm just dragging all of those names into the global namespace. So then I can refer to anything that lives in namespace stood unqualified. And the way this works is unqualified name lookup has a rule that it says, okay, first I'm going to search for everything that really exists in the global namespace, like all of the stuff in the C standard library, size T and whatever. And then if there's any using directives, I'm going to go search those namespaces too. And the way the standard's written, that search is transitive. So if I say using namespace X, and X, the namespace itself contains a using directive for namespace Y, I'm also going to go search namespace Y. Usually, in most programs, using directives are just put at the global scope because people just want to use all those names. But you can also put them within other namespaces, or you can make them local to a function. That way, the using directives effect is confined for the duration of that function, and it won't leak out and affect other code. Whereas a using declaration is very targeted. If I'm at global scope and I say using stood vector, that will drag the name vector only into the global namespace, and I can refer to that unqualified, but it will not drag in stood DAC and stood list and whatever. However, argument-dependent lookup is still applicable, so I could call algorithms on vector if the vector type itself is the argument. In that case, it'll search namespace stood. Whether that's a good idea or not, that's sort of up to your style. Personally, I don't like to use ADL except when I really want it, like in the case of overloaded operators or calling swap unqualified. Otherwise, I would much rather explicitly qualify the call or just have it using directive for the whole thing. I don't like to rely on ADL if I don't have to. So that's the difference between using directives and using declarations. Now, going on into something more advanced, if I have a using directive, it makes the name visible, but the class still really lives in that namespace. So here I'm going to get rid of the standard library. Okay, so now I have nuked all my standard library code, my hello world. Because we're using the core language, I don't need to include any headers. I will, however, include standard.io.h, or studio as I pronounce it, because I just want to print some stuff, but this is no relation to the actual code that I'm working with. So imagine that I have a primary template. Skipping ahead to clause 14, a primary template is when I have something like template, type name t, struct meow. This is for an arbitrary t, I don't know what it is yet. And I have a member function void per, and here I just want to print something proving that I'm calling it. So puts meow of t per. And then I would like to specialize it. When I cover clause 14, you'll see all the wonderful things you can do with explicit and partial specializations. I want a meow that's just for int. In this case, I'm going to have a per where I will prove that I'm invoking meow of int per. Like this. Yeah, stop that. Then in my main, I will have meow of long L, L per, meow of int, I per. And I want a breakpoint here. And compile, bam. So this does prove that yes, meow long will call the primary templates meow t per, and meow int will call this explicit specialization meow int. So here I've put it in the global namespace because it's just a toy example, but what if I had this in an actual namespace imitating somewhat more closely real library code? So I could say, okay, I'm going to put this in a namespace foo, like this, and I will then indent all this stuff, and then close the namespace, and then this will not compile. In fact, the squiggle will tell me identifier meow is undefined because I put this in namespace foo. So in main, I could either qualify foo meow or, hey, let's try a using declaration. So I could say using foo meow. Okay, and I'll save. The squiggles go away. So I laid out the order in which things happen. This is true also for classes, even though things like template argument reduction, overload resolution don't apply to classes. When I say meow long, the compiler needs to know what meow I want because it's a class template name. So it needs to go look up meow. When I say using foo meow, I'm dragging in the name foo meow into main. This will exist only for the scope of main. If I try to refer to meow outside of this function, I'll need to qualify it or have another using declaration. And then I can refer to meow of long and meow of int, and the compiler knows that, oh, this is a class template, and I'm not trying to use operator less than or anything strange here. And I'm dragging in only the name. I don't say anything like using foo meow long or whatever, because I'm not talking about the class, I'm only talking about the name. Name lookup could really care less what the meow is. To it, it's just a name. So this will, forget if I compiled this or not, this will compile and run because I've dragged in foo meow, and the puts is slightly wrong because it really should say foo meow t. In fact, I can go fix that. If I say foo, to be precise, there's a C99 feature, double_ function, something like that, that allows you to have a macro that expands to some version of the current function's name. I believe we actually have that in VC, but it goes by like 3 different non-standard names, and I have to go look them up in MSDN. So rather than trying to do that from memory, I'll just have these puts here. So this is what it looks like if you have an explicit specialization within a namespace. But what if I had this explicit specialization outside of namespace foo? So that would look like this. I close foo here, and I unindent like this. Okay, so this will fail to compile. You can see it's already squiggling because it doesn't know what meow is. In order to explicitly specialize a template, it needs to see the primary. The primary is foo meow, and if I go out to global, then, hey, what meow is this? So I could say foo meow like this, in which case it will compile and run as usual. That's not the one I want. Here we go, as expected. But now imagine that I've got using declarations. So if I say something like this, suppose that I'm in namespace. Let's see, what scheme do I want? Yeah, I'll put it in a subnamespace. So if I have a namespace bar, okay. Before I get too crazy, I'll go like this. And this is foobar meow. And then outside here, I'm going to using bar meow. Okay. And this should compile. It does. And why did it not run? There we go. Yes. So what I've done here is I have an outer namespace foo and an inner namespace bar. And then I have a primary template, foo bar meow, and an explicit specialization, foo bar meow of int. And then I close namespace bar. So I'm done with that. And in the outer namespace foo, I say using bar meow. So I'm dragging in the inner namespace meow into the outer namespace. So that means when I'm in main, I can say using foo meow and pretend that I defined it all along in that outer namespace. And what this does is says, okay, I want foo meow. Let's go look in foo. I don't have a meow here, but wait, there's a using declaration for bar meow. Let's go look in bar. Oh, here it is. And here's the explicit specialization. Let's go invoke this. So that all works. Now imagine that I didn't put the explicit specialization here, but instead I try to put it out here. And I said foo meow int ID tab, save, like this. So in this case, if I say foo meow of int, then it's going to look for foo. Oh, and it finds this using declaration, and then it knows that I'm specializing this primary template here. So this will actually build and run. There we go. Yes, for some reason I had forgotten the rules and I thought that this should fail to compile, but I'm like 90% sure the VC is doing the right thing here that I'm going to explain. So in going back to VC in the standard library, we had added the TR1 additions in VC9 SP1, and those lived in the subnamespace std TR1. And in C++ 11, things like std TR1 shared putter and std TR1 function were promoted, and they became real members of namespace std. Yet in VC10 SP1, we didn't have time to, and VC10 RTM as well, we didn't have time to go change over all of the namespaces, so we did a shortcut. While still defining shared putter and function and other helpers in namespace std TR1, we then drag them out into namespace std with using using declarations, just like this using foo meow. So to almost all uses, it looked like they really live in namespace std, even though their true name was in std TR1. In VC11, we've switched that around. Now, shared putter and function and so forth, all these things that originally lived in the TR1 subnamespace, they're now truly defined in namespace std. And then for backwards compatibility, we drag them into TR1, std TR1, so that if you have old code meaning around 2005, 2008 vintage, that's referring to names in TR1, it'll still compile. And that's all done through these using declarations. Now you can tell the difference if you look at types in like the debugger, or if you're looking at mangled names, because that will always refer to the true name that something was defined in. The other way you can tell the difference, I had not shown argument-dependent lookup here, but the way argument-dependent lookup works is it will search only the namespace that something was defined in. In fact, I should be able to present that. If here I can just get rid of all this template stuff. So if I have just a struct meow, and I have foobar meow per, yes, and a using bar meow, that'll work. And doesn't need to be a template here, m. I'll do it with a non-member function like this. You don't want to run. Okay, and here, per should be a non-member function. Here I just want an empty struct to serve as a type. Yes. If I have a void per, taking a const meow ref, doesn't really need to be const, and I'm going to put that I am a foo bar per, like this. Okay. So this is invoking argument-dependent lookup to find foobar per that lives in the same space as meow. And in fact, I don't need this using directive here. I can just say foobar meow like this. Save, execute. Foobar per, like that. Now, here I defined the function per in the exact same namespace as where meow lives. Its true name. But it's also visible as just plain old foo, meow. So this will still compile. If I refer to it as foo meow, because this will look in namespace foo, find the using declaration, and then find this meow here, and then argument-dependent lookup will find the associated per. So this will still compile and run, like that. However, if I attempted to find this per not in the true namespace of meow, but if I put it in the namespace that appears to live in foo, it won't work anymore. So that would look like this. Okay. Now let's page down. Fails to compile. Here it's complaining, oh, identifier not found. On line 17, it doesn't know what per I'm trying to call. Line 17 is in main here. Yep, that's line 17. So what's going on here is I have this outer namespace foo, inner namespace bar, struct meow. I've dragged the name meow into my outer namespace foo, and then I define a per function. Up till now, I'm still totally cool. I take a const meow, and it knows which meow this is, because I've got a using declaration. So foo per will take foobar meow. That's fine. This, however, is no longer accurate. The problem is when I go into main. So up to this line, everything is still cool. I say foo meow, and that finds, it traverses this using declaration, finds the inner one. Then I try to do argument-dependent lookup, finding this per. So argument-dependent lookup's rules say it will search, in addition to unqualified name lookup, only the true namespace in which an argument lives. It won't search namespaces in which the thing appears to live. So even though meow appears to live in the outer namespace foo, its true name is foobar. So that means ADL will not find this thing sitting in the outer namespace. It will search the namespace bar, but aside from this struct, that's completely empty. So that's why it fails to compile. This is one case in which C++ cares about the true namespace that something lives in. And this is actually a good thing. Argument-dependent lookup, it's adding extra things to the overload set. You want to find functions that are tightly associated with a class, but you don't just want to start adding in any old thing. Because these are sort of unconditionally added whenever you've got an unqualified call. It wants to be very precise. This sort of limits the possible damage that it could cause. Yet if you start getting crazy with using declarations, you need to be aware of this rule, that it will only search the associated namespace like this. So this is one of the ways programmers could be broken by our dance with std and tr1 and vc10 and vc11 if they were depending on something living in TR1 to only drag in functions that were living in TR1 and not functions living in std. Well, now everything lives in std. Or vice versa. Now people can depend on std shared putter dragging in through ADL other functions that live in std, even though maybe they shouldn't. So that wraps up name lookup. In future segments, I'll be going through things like template argument deduction, overload resolution, and any other topics in the core language you'd like to see. Drop a note in the comments if there's any issue you'd like me to talk about. See you then.